Welcome back. In today's video, we want to find the current through the inductor using the phasor domain analysis technique. In the previous video, we did the same thing. However, in that video, we found the current through a capacitor. So in today's video, we replace that capacitor with a inductor. So we can go ahead and do that. As always, we adopt the positive cosine format. Our source current is in a positive cosine format. So second step, we can then transform our circuit from the time domain to the phasor domain. We transform all time dependent sources and our capacitors and inductors. So we can go ahead. The phasor component for our current source is equal to magnitude of 12 times e to the minus 60 degrees. And our impedance for inductor is equal to j omega L. So that is j times 2 pi times 10 to the power 4 times 0.5 millihenry. So let's just do this like that. Minus 3. This equals to a positive j 31.4 ohms. So that's positive and real. And we can go ahead. You could do any method you want. The simplest method right now, because we have two components in parallel, we can apply current division. So thus, if we apply current division, we can say the current through the inductor IL is equal to the current source IS times the resistance divided by the same resistance plus the impedance of the inductor. This equals 2. And if you can go ahead and just say, you can just place your current in. So you can say 12 times the complex exponential e to the j 60 times a resistance of 20 ohms. And our current is in milliamperes, so we want to put an e minus 3 there. Our bottom, the resistance is still 20 plus a positive j 31.4 ohms. So we can go ahead, convert our denominator into polar form so we can divide easily. The numerator simplifies to 0.24 times the complex exponential e to the j 60 degrees. We apply our complex algebra properties to simplify our denominator from rectangular form to polar form. So we take the positive square root of 20 square plus 31.4 square. We get a magnitude of 37.23. And then we e to the j, and theta is now inverse tangent 31.4 divided by 20, which gives an angle of 57.5 degrees. Then, because this is in polar form, easier to divide, so we can divide out and we get 6.45 or just 6.5, or just let's keep 2 digits, so 2 decimal places. So 6.45 times the complex exponential e to the j minus 117.5. And that's in degrees. Then we can go ahead and transform that back into the time domain by using our time domain relationship, so our time to phasor domain relationship. So that's 6.45 cosine 2 pi times 10 to the 4 times t minus 117.5 degrees. And that's in milliamps. So the current through the inductor is equal to the following. The relationship that I use to transform the current through the inductor from the phasor domain to the time domain is the relationship. If we have a signal x of t that is equal to a times cosine omega t plus theta, we can transform that to the phasor domain, and that is going to equal to the phasor component x, which is equal to a times the complex exponential e to the j theta. for our complex algebra properties that we use in the denominator. That is the positive square root of x squared plus y squared is equal to our magnitude. And if you want to use x or z, doesn't matter. And then we have that x, our phasor component x is equal to x, the magnitude of x times the complex exponential e to the j theta. Theta is equal to inverse tangent y over x. And basically that's all we used for our complex algebra. Okay, so that's it for today's video. See you in the next one. Bye.